In this video, we're going to focus on radical operations. So we'll add and subtract radical expressions, then we'll multiply radical expressions, and we'll finish up by dividing radical expressions. In order to add or subtract radical expressions, both the index and the radicand, that's the number underneath the radical, have to be identical. Don't judge whether or not you can add or subtract them before you have simplified all of your radicals. So to simplify 32, we would use 8 and 4. Then we could use 2 and 4 and 2 and 2. And our other 4 would also be another 2 and 2. There's already a 5 in front. And since the index is 2, we would take groups of 2 of the same number out. So I have one group of 2, and here's another group of 2 that can come out to join the 5. And I'm left with a 2 inside of the radical. For 27, our factor tree would use 3 and 9, and then 3 and 3. Once again, an index of 2 means I need 2 of the same number to come out. So minus one group of 3 and another 3 that has to remain inside the radical. Minus and a 2 that's already out, and a 75 needs a factor tree. 3 and 25, 5 and 5. 2 of the same number because the index is 2. So 5 will come out, and a 3 will remain. We can simplify the numbers in front by multiplying 5 times 2 times 2, which gives me 20 square roots of 2, minus 3 square roots of 3, and then finally 2 times 5 would give me 10, so minus 10 square roots of 3. From there, we can easily see that there are two terms that have the same radicand and the same index. So our 20 square root of 2 will remain the same, but we'll have negative 3 square roots of 3 minus 10 more square roots of 3 gives me negative 13 square roots of 3. We treat that radical kind of like it's a variable. It doesn't change when we add or subtract it. Only the coefficient in front changes. For number 2, we once again needs to simplify each of the radicals. So we'll have a 9 that comes down in front, and the 12, we could use 3 and 4, and then 2 and 2. Since it's an index of 2, we'll bring down a pair of 2's to join the 9, and 3 will remain inside. For the next one, I can use 4 and 8, 2 and 2, and 2 and 4, and then 2 and 2 for my prime factorization. A pair of 2's can come down and join the 5 that was already there. And here's another pair of 2's that can come down and join, leaving 1, 2 stuck inside. Finally, for 72, we could use 8 and 9, 2 and 4, 2 and 2, and 9 would be 3 and 3. A pair of 2's will come out front. Here's a pair of 3's to join it, and a 2 will remain. So we'll multiply those coefficients in front. 9 and 2 gives me 18 square roots of 3. 5 times 2 times 2 gives me 20 square roots of 2, minus 2 times 3, which is 6 square roots of 2. We can see that we have two terms that have the same index and same radicand. So 20 square roots of 2 minus 6 square roots of 2 gives me a total of 14 square roots of 2. And the 18 will just continue to be brought down in front. For multiplying radical expressions, we don't need to have the same radicand, only the same index. So when I see two separate square roots, they both have an index of 2, I can write them underneath a single square root. So we'll have a 4 in front of our square root, but these are both index of 2. So I can write one single square root, and do 5 times 125, which if you'd like, you can simplify that to 625, or you can leave it separate for your factor tree since you would break it down anyway. And then a to the 5th and a to the 3rd. We add exponents when we multiply, so that becomes a to the 8th. To do a factor tree, I have a 5 already, and joining it will be 125's 5 and 25, and then 5 and 5. This has an index of 2, so the 4 comes out in front, and I'll have one group of 5's, and here's another group of 5's. And then for our a to the 8th, we take our exponent, divide it by our index. 2 goes into 8 4 times with no remainder. So a to the 4th would come out, and I don't have anything left over inside the radical. So 4 times 5 times 5 gives me 100 a to the 4th. Number 2, these are both 4th roots, so I can write a single 4th root symbol. And 3 and 27 will be multiplied. X to the 3rd times x gives me x to the 4th, and y squared times y squared gives me y to the 4th. Complete a factor tree for all of the numbers. 9 and 3, 3 and 3. Since it's the 4th root, I need to have 4 3's to be able to come out of the radical. So only one group of 3's can come out. And the exponent is 4, divided by the index, which was also 4. 4 goes into 4 one time with no remainder. So x will come out, and then the same thing will happen with y. When we introduce addition and subtraction symbols, we have to introduce the idea of foiling with radicals. So I'll need to draw my 2 by 2 box and multiply 4 and 2 square roots of 5 and 3 square roots of 3 plus 4 square roots of 5. When you multiply these, the numbers in front will multiply, and the numbers inside the radical, the radicand, will multiply. So 4 times 3 gives me 12, and then the square root of 3. 2 times 3 gives me 6, and the square root of 3 times the square root of 5 will give me the square root of 15. 4 times 4 gives me 16, and then I have a square root of 5. 2 times 4 gives me 8. The square root of 5 times the square root of 5 was the square root of 25, or just 5. So inside this box alone, I have 8 times 5, which is 40. Make sure that each of your radicals are simplified as far as possible. Underneath this radical, I have a 3. That can't go any further. I have 16 square roots of 5. That can't be simplified any further. And 6 square roots of 15. Since the only thing that multiplies to be 15 is 3 and 5, there's no pairs, so it can't go any further either. Then plus our 40. There's our answer. Remember that when something is squared, it means something times itself. So you cannot just square each of these and simplify. You have to draw your box again and multiply them out. So we'll have square root of 5 minus the square root of 11 times square root of 5 minus the square root of 11. Square root of 5 times the square root of 5 is just 5. Square root of 5 times negative square root of 11. The negative will come down, and the 5 and 11 will become 55 under the radical. Same thing will happen here, another negative square root of 55. The negative times the negative will change to positive, and the square root of 11 times the square root of 11 is just 11. So when I go to simplify, I'll have 5 plus 11, which is 16. Negative 1 square root of 55 minus 1 square root of 55 gives me negative 2 square roots of 55. Number 5. The difference here between number 4 and number 5 is that, yes, these are the same numbers, but instead of being squared, they actually have different signs in the middle. This is what we call conjugates, and they'll be incredibly useful when we are dividing radicals on the next page. So you'll still draw your box when you multiply these. We have 8 square roots of 3 minus 2 square roots of 2, and 8 square roots of 3 minus 2 square roots of 2. Oops, that one's plus 2 square roots of 2. 8 times 8 gives me 64, and the square root of 3 times the square root of 3 is just 3. Negative 2 times 8 is negative 16. Square root of 2 times the square root of 3, we'd multiply the 2 and 3 to get 6. So square root of 6. 8 times 2 gives me positive 16, and the square root of 3 times the square root of 2 gives me the square root of 6. Negative 2 times positive 2 gives me negative 4, and the square root of 2 times the square root of 2 is just 2. We've got a couple of boxes that can simplify further. 64 times 3 is 192. Negative 4 times 2 gives me negative 8. 192 minus 8 gives me 184. Negative 16 square roots of 6 plus 16 square roots of 6, those will cancel. And so my final answer is just 184. This is useful for when we have a radical in the denominator and we need to be able to get rid of it. We can multiply something by its conjugate and we get rid of all the radicals. We did a similar process when we did i's in the denominator and had to multiply by a complex conjugate. Before we jump into that, let's look at a more simple rationalization of the denominator. Before you rationalize a denominator, I always think it's a good idea to try to simplify first because there may not be a need to rationalize. For this example, we have the exponent is 5 and the index is 2. 2 goes into 5 twice with 1 remaining. So outside of the radical, I'll have c squared and I'll have 1c remaining inside. Then we have d to the 9th and an index of 2. 2 goes into 9 4 times with 1 remaining. So outside of the radical, I'll have d to the 4th. Inside the radical, I'll have 1d. So unfortunately, we did not get rid of all of the square roots. We needed to be able to have another pair to come outside of the square root. So the issue that we have is a radical in the denominator. That's what's keeping us back from being simplified. Since it has an index of 2, we would need to have 2 d's to come outside of the radical. I only have 1 d, so if I multiply by 1 more d underneath the radical, I would be able to get rid of the radical altogether. I can't just multiply on the bottom. I have to multiply by the exact same thing on the top so that I don't change the value of this fraction. You've done something similar to this back when you had to find common denominators when you were adding and subtracting fractions. So I have c squared on top. C times d will go underneath one of the square roots. Then on the bottom, I have d to the 4th. And now I have the square root of d times the square root of d. I've got the 2 d's that I need to be able to come outside of the radical. So I have a total of d to the 5th on the bottom. And on the top, we'll leave it as c squared square root of cd. You cannot simplify these d's. It is protected underneath this radical. For number 2, this time we have a 4th root. In a 4th root, we must have 4 of the same number in order to come out. So the first thing that I'm going to do is separate these out into two separate radicals, because sometimes that helps me simplify further and maybe I won't need to rationalize. So unfortunately, I can't simplify any further on the top, but I don't care if there's radicals on the top. The problem is that I have a radical on the bottom and I can't simplify any further. You may want to take this 8 and do a factor tree with it though. 4 and 2 and 2 and 2. When I do the factor tree this way, I can see that I have 3 2's already. Remember, I needed a group of 4 if I wanted it to escape outside of the radical. So I can multiply by one more 2, and if I do that on top and bottom, I'm not changing the actual value of my fraction, and it will give me the fourth 2 that I need to be able to escape that radical in the denominator. We're going to do the same thing with the y. I need 4 y's in order for them to escape the radical. I already have 1, so if I had 3 more, I would be able to escape the radical. So on the top, I'd have the fourth root of 5 times 2, which is 10. There's an x and a y cubed. On the bottom, I now have a total of 4 2's. 3 of them are from the 8, and here's the fourth. So they'll come out as one group of 2, and I have a group of 4 y's. So they'll come out as a group of y. You cannot simplify the 10 and 2 or cancel out any of the y's. For number 3, we can't just multiply by the square root of 3 on top and bottom, because we would have to distribute that inside and it would give us a square root still on the denominator. So instead, we'll multiply by the conjugate. So we're multiplying the top and the bottom by the same numbers as the bottom, 2 and square root of 3, but instead this time of being plus, it'll be 2 minus the square root of 3. Now the 5 can just be distributed, which leaves me with 10 minus 5 square roots of 3. But the bottom we'll need to do FOIL with, or boxes. 2 plus the square root of 3 and 2 minus the square root of 3. 2 times 2 gives me 4. 2 times the square root of 3, 2 square roots of 3. 2 times negative square root of 3, negative 2 square roots of 3. 3 square root of 3 times negative square root of 3 gives me negative, and square root of 3 and square root of 3 is just 3. So I'll have 2 square roots of 3 minus 2 square roots of 3 that cancel, and that takes care of all of my radicals. Just simplify the last two numbers. 4 minus 3, which is 1. So you can write this as over 1, or recognize that over 1 doesn't change anything. This is my answer. For number 4, we need to get rid of this radical. So we're going to be multiplying the top and the bottom by the conjugate of the bottom. So square root of 3 minus 4. This time, we'll need to draw two sets of boxes, one for the top FOIL and one for the bottom FOIL. So we'll have 6 minus the square root of 3 and the square root of 3 minus 4. And then for the bottom, we'll have the square root of 3 plus 4 and the square root of 3 minus 4. Multiply the insides. So 6 square roots of 3, negative 3, negative 24, and negative square root of 3 times negative 4 is positive 4 square roots of 3. These two will combine together to be 24 square roots of 3. These two will combine together to be negative 27. Then across the bottom, square root of 3 times the square root of 3 gives me just 3. Then 4 times the square root of 3, negative 4 times the square root of 3, and negative 16. The 4 square root of 3 and the negative 4 square root of 3 will cancel. And I have 3 and negative 16, which gives me negative 13. Always check to make sure that the coefficients can't cancel or reduce in any way, and they can't. So this would be my answer. In the next problem, I have a square root, so my index is 2. And so I have 5, which can't be broken down any further with a factor tree, and I have y, which can't be broken down any further with a factor tree. So since it's a square root, we'll make a square root on top and a square root on the bottom. Then we need 2 total 5s in order for them to come out of the radical, and I already have 1, so I'll multiply by 1 more on top and bottom. We need 2 total y's in order for them to come out of the radical, and I already have 1, so I'll multiply by 1 more on top and bottom. On the top, I have 10y under the square root, and on the bottom, I have square root of 5y times the square root of 5y. I now have the pairs that I need to be able to come out. For number 6, I have a 4th root, which means if I want enough for anything to come out, I have to have 4 of them. So I'll break it up into 2 separate radicals. Unfortunately, if I were to do a factor tree for the 8, I would have 2 and 4 and 2 and 2. That's not enough for it to come outside of the radical. And then the 9, a factor tree for that, would give me just 2 3's. And in order for them to come outside of the radical, I need a total of 4. So if I need 4 and I already have 2, I can multiply by 2 more 3's on top and on the bottom. For the a's, I have 3 a's and I need 4 altogether. So if I multiply by 1 more a on top and bottom, I will have the 4 that I need. So I have a total of 4 3's on the bottom now, so they will get to come out, and a total of 4 a's, so they will get to come out. And the top, I have 8 times 3 squared, which is 72, and an a on top. For number 7, find the altitude of the triangle if the area is 189 plus 4 square roots of 3 square centimeters. Remember that area is the base times the height divided by 2. So let's fill in the information that we know. We know that the area is 189 plus 4 square roots of 3. We know that the base of the triangle is 12 plus square root of 3. We need to multiply that by the height and then divide it by 2. So we are solving for the height. That is our altitude. So the first thing that I need to do is multiply by 2 on both sides. That will require me to distribute my 2 across to both terms. So 189 times 2 gives me 378 plus 8 square roots of 3 equals 12 plus the square root of 3 times h. If I want to get h alone, the next step would be to divide both sides by 12 plus the square root of 3. So we're left with a similar situation that we just saw in number 3 and 4. I have a radical on the bottom. So to get rid of the radical on the bottom, I would need to multiply both the top and the bottom by the conjugate, 12 minus the square root of 3. That's going to require 2 boxes. So here's my first box. And I'll do 12 minus the square root of 3 times 378 plus 8 square roots of 3. So 378 times 12 gives me 4,536. Then minus 378 square roots of 3. These two will multiply together, 8 times 12 to give me 96, and then the square root of 3, and then negative 8, and the square root of 3 times the square root of 3 would give me just 3. So inside of this box would become negative 24. So if we were to simplify this, we would have 4,536 minus 24, or 4,512, and then my negative 378 square roots of 3 plus my 96 square roots of 3 would give me negative 282 square roots of 3. Now for our second box. That would be what we had on the bottom. So here's our box. We have 12 plus the square root of 3 and 12 minus the square root of 3. 12 times 12 gives me 144. Then 12 square roots of 3, negative 12 square roots of 3, and this becomes negative 3. So 144 minus 3 is 141. Now we want to check to see if 4,512 and 141 and 282 can all be reduced by something. And they all can. They can all be reduced by 141. So I will write my answer over here because I kind of didn't plan that out very well. So I'm going to put my answer in here. 4,512 divided by 141 is 32, minus 282 divided by 141 is just 2. And of course, we already had the 141 divided by 141, which is just 141. So what's the length? It is 3 minus 2 square roots of 3 centimeters.